Now let us look at the next problem. Shown in the figure below is a meter bridge set up with null deflection in the galvanometer. The value of the unknown resistance R is. Now the balancing of meter bridge means that there is no current flowing through the galvanometer. That means the ratio of the resistance is equal to the ratio of the lengths. Okay, so this is based on the principle of balanced Wheatstone bridge. So this problem is a very simple one. 55 by R will be equal to length L1, which is 20, upon length L2, which is 80. 100 minus 20 is 80. So this is 1 by 4. R is equal to 55 times 4. This is equal to 220 ohms. This is the answer. Now let us look at the next problem. A thin rod of length L is lying below the x-axis, lying along the x-axis with its end at x equal to 0 and x equal to L. Its linear density, that is mass per unit length, varies with x as x by L to the power n, where n can be 0 or any positive number. If the position xcm of the center of mass of the rod is plotted against n, which of the following graph best approximates the dependence of xcm on n? Now the situation is something like this. You have a thin rod of length L. One end is kept at x equal to 0, another is kept at x equal to L, and the linear density lambda, that is, if you wish to find out the density or the mass per unit length at this point, then this lambda is given by x by L to the power n, where n can be 0 or any positive number. Now this much is given to us. We have to find out among the 4 graphs that are given which one best approximates center of mass with number n. Okay, now we know that center of mass xcom will be given by integral of, because this is a continuous mass distribution system, so we have to apply the concept of integration of moment of mass, which is dm into x divided by dm. Okay, now if we take a small element at a distance x having length dx, its mass dm will be given by lambda times dx. Okay, and lambda is x by L to the power n. Okay, so if we substitute the values over here, we will get integral of dm will become x to the power n divided by L to the power n x dx, and the denominator will become x to the power n upon L to the power n dx. So if we take L to the power n common, which is a constant, so they will cancel out each other, and the remaining expression would be x to the power n plus 1, x to the power n, and x will become n plus 1 dx, and denominator will become x to the power n dx. Okay, now this will be equal to x to the power n plus 2 divided by n plus 2, and denominator will be x to the power n plus 1 divided by n plus 1. This can be written as x times n plus 1 divided by n by 2. Okay, now we have not applied the limits in the integral. The limits are from x equal to 0 to x equal to L. So the limits are 0 to L, 0 to L. Okay, now since the limits were same, that is why if you substitute the values over here, 0 to L and 0 to L, this will become L to the power n plus 2 and divided by L to the power n plus 1. So this x can be replaced by L. So the final center of mass expression will be n plus 1 divided by n plus 2 times L. Okay, now if we take different values of n as 0, 1, 2, 3, we'll get the value of xcom as L by 2, 2L by 3, 3L by 4, and so on. Now we can see that as n tends to infinity, x tends to L, and it is gradually increasing from L equal to x equal to L by 2. So if you plot the curve, for n equal to 0 the value is L by 2, and for n is equal to infinity this will become L. Okay, so if we look at the four options that are given to us, option A is correct.